Welcome to this video in which we will describe how to find the equivalent resistance of two parallel resistors and then extend that to multiple or more than two parallel resistors. So the first thing we need to do is talk about equivalence. If you've already looked at the equivalent resistance for series resistors, then this will be a little bit of a review. But the question is, how can we say that a single resistor, in this case, R equivalent, is equivalent to this parallel combination of the 3 ohm and the 6 ohm resistor? And the way we say that two resistors, or in fact any two circuit elements, are equivalent is that the rest of the circuit, that's basically all this stuff out here that's connected to these two resistors, or that's connected to the equivalent resistance, sees the same voltage current characteristics for both. In other words, the VI characteristics for this parallel combination are exactly the same as the VI characteristics for this equivalent resistance. And that means that the rest of the circuit couldn't tell if it's hooked up to the parallel resistors or the equivalent resistors. So that's basically the idea. What we'll do is we'll use this example of a 3 ohm resistor and a 6 ohm resistor in parallel to develop the concept, and then we'll generalize it and to two general resistors and then to more than two resistors. Okay, so if I look at the equivalent resistance, the relationship between voltage and current is given by Ohm's law. V is Ri. Now, I need to find a similar relationship for the parallel resistors, and this is actually going to be a little bit tricky. So we'll actually have to do some algebra to get this. So bear with me. It's good for your soul. So we'll define, we'll call this I1, the current through the 3 ohm resistor, and I2, the current through the 6 ohm resistor. We know that the voltage across both resistors is the same because they are both connected between the same two nodes. That's also how we know that they're parallel resistors, is that they're connected between this node and this node. And resistors are parallel if they're connected between the same two nodes. Okay, so the voltage across both resistors is the same, and we've labeled it as V, as this guy here. So what that means is we can say that I1 is equal to the voltage V divided by 3 ohms. I2 is the voltage V divided by 6 ohms. Okay, now if we apply Kirchhoff's current law to the top node, we have the current I going in, and that's equal to the sum of the currents leaving, which in this case would be I1 plus I2. Okay, and so we can use these two expressions for I1 and I2 that we've just developed to say that this is going to be V over 3 ohms plus V over 6 ohms. Now we can factor out this V from both terms as V times 1 over 3 ohms plus 1 over 6 ohms. Okay? Now to get this in the form of V is equal to something times I, which we want to do because that something, if we can find it, will be the equivalent resistance. We divide both sides of this equation that relates I and V by this term. And then we end up with V. Whoops, I don't know why I underlined that. V is equal to 1 over 3 ohms plus 1 over 6 ohms times I. And believe it or not, this is pretty much what we want, because we have V is equal to something, and this something is this fraction times I. So that basically gives us what our equivalent is in this case. Now, if you wanted to, you could go ahead and plug all this into a calculator and work it out, but I'd actually like to simplify this expression right here. So to do that, let's clear out a bit of space here. We'll nuke the equivalent resistance side. And what we will do, we'll still have the 1 over, and then we'll have 1 over 3 ohms. What I'm going to do is take the 1 over 3 ohms and the 1 over 6 ohms and put them over a common denominator, and then the 1 over that we'll just end up flipping the fraction that I get down here for the denominator, if that made sense. Hopefully, if it didn't make sense, it'll make sense by the time we're done. So I'm going to take 1 over 3 ohms and multiply it by 6 ohms over 6 ohms, which I can do because 6 ohms over 6 ohms is 1. Then take the 1 over 6 ohms and multiply it by 3 ohms over 3 ohms. Okay, so now both of these have the same denominator, which is 3 ohms times 6 ohms. The top one here is just going to be 6 ohms because I'm multiplying it by 1, and the top here is going to be 3 ohms. So I can rewrite this as 1 over my 6 ohms, this guy, plus my 3 ohms, this guy, over the product of 3 ohms and 6 ohms. That's this guy. And now 1 over this fraction is just going to be the inverse of this fraction, which is 3 ohms times 6 ohms over 6 ohms plus 3 ohms. Okay, so this is actually a much nicer formula to work with. It basically gives me now the equivalent resistance of these two parallel resistors. And if I work out the math, the top ends up being 18 and the bottom ends up being 9. 18 divided by 9 is 2 ohms. So in this example, I know that the equivalent resistance of these two parallel resistors is 2 ohms. And again, it's equivalent in the sense that the rest of the circuit would act exactly the same if I had a single 2 ohm resistor connected to it as it would if I had a 3 ohm and a 6 ohm resistor in parallel connected to it. So let's generalize this a little bit. If we have 2 resistors in parallel, the equivalent resistance is given by R1 times R2 over R1 plus R2. Okay, and just to make sure that it's clear, we can do it the other way. That's just a little messier. It's 1 over R1 plus 1 over R2. And I bring this up for a specific reason. Suppose that we have 3 resistors in parallel. R1, R2, and R3. Okay. The equivalent resistance here, we'll write that in green so you can tell the difference between the two. Okay, the equivalent resistance here is given by 1 over R1 plus 1 over R2 plus 1 over R3. Okay, and that's not that hard to compute. But the temptation is to take this expression, which is kind of nasty looking, and try to turn it into something that looks like this. And almost invariably what people try to do is write it as R1 times R2 times R3 over R1 plus R2 plus R3. And while it looks like that should work, it turns out that it's absolutely wrong. So this is not equal to. There is an expression that you can get, but it turns out to be actually more complicated than just using this 1 over R1 plus 1 over R2 plus 1 over R3 expression. So if you're tempted to do this, don't. Stop now. Forget it. Don't even try it. So that pretty much describes the computation of equivalent resistances with parallel resistors. And in subsequent videos, we'll have some examples where we simplify complex resistor networks into a single equivalent resistor. And that will hopefully give you some application of these principles. So thanks for watching, and hope it's been useful.